Hey everyone! So, you've got these lecture notes on cryptography, specifically TLS 1.3 key derivation, and yeah, it can be a lot. You're probably staring at these complex diagrams and acronyms and feeling a bit lost. Well, you're in exactly the right place. We're going to take all that complexity and break it down step by step into something that actually makes sense. Let's dive in.
Just think about that for a second. How is it even possible that your computer and some random website server, two total strangers, can just start sharing secrets privately? It seems like it should be impossible, right? Kind of feels like magic. But it's not magic. It's just a really, really clever process. A special structured conversation that happens before the real conversation can begin.
And that special conversation has a name, the TLS handshake. Before a single piece of your important data gets sent anywhere, your browser, the client, and the website server perform this little dance. They say hello, they check each other's IDs to make sure they are who they claim to be, and this is the crucial part. They agree on the secret keys they're going to use to encrypt everything. This negotiation is the bedrock of the entire secure connection.
Okay, so here's our game plan. We'll start with the handshake problem, then we'll decode the key blueprint. After that, we'll look at the initial shared secret, the keys that protect the handshake, and then the keys that protect your actual data. And finally, we'll wrap up with why this whole recipe is just so effective.
All right, let's get right to the heart of it. The best way to understand how these keys are made is to think of it not as a single action, but as following a very specific, very precise cryptographic recipe. Every single ingredient and every single step is there for one reason: maximum security.
Now, let's be honest. When you first see a diagram like this in your notes, your first thought is probably something like, whoa, what is even happening here? It just looks like a crazy mess of boxes and arrows and acronyms. It's super intimidating. But I promise you, we are going to walk through this one piece at a time, and you'll see it's just a logical flow, one secret leading to the next. It's all going to make sense.
You know, every process has to start somewhere, and for all the incredible security that follows, it all hinges on one foundational moment: the creation of a single initial secret that both the client and the server can agree on, without ever actually sending it across the internet.
So how on earth do they do that? Well, first, they agree on a method, usually something called ECDHE. Don't worry about the full name, it's just a really clever mathematical trick. Here's the gist. They exchange some public information, stuff that's totally safe for anyone to see. Then, by combining that public info with their own private secrets, both sides can independently calculate the exact same secret number. That secret is never transmitted. It's just born on both sides at the same time, and it becomes the seed for every other key we're about to make. Okay, so now we have our one starting secret. But the thing is, we need a whole bunch of different keys for different jobs. So how do we get them? We use a special tool called HKDF. And the easiest way to think of HKDF is as a secret key multiplier. It's like a cryptographic machine. You put one strong secret in the top, and it can safely generate a whole series of new, unique, and equally strong secrets. It's the magic mixer in our security recipe.
All right, on to phase one of our recipe. Now, before we can even think about protecting your actual data, we have to protect the negotiation itself. It's kind of a weird problem, right? We need to have a private conversation about how to have a future private conversation. So the very first thing we have to do is create keys just for this initial setup.
And the process is actually pretty straightforward. We take that initial shared secret we just made, and we feed it into our HKDF mixer. The first thing that comes out is a new secret called the handshake secret. Then we take that handshake secret and immediately feed it right back into the machine to create two more, even more specialized types of keys. So let's go back to our blueprint and trace this path. You see that initial shared secret at the top? That's used to create the handshake secret, which is labeled HS here. Now just follow the arrows down from HS. It's used to produce CHTS and SHTS. These acronyms just stand for Client Handshake Traffic Secret and Server Handshake Traffic Secret. These are the keys that will protect this initial conversation. So what are their specific jobs? Well, the handshake traffic secrets do exactly what their name implies. They encrypt the back and forth messages of the handshake itself to keep that negotiation private. Then you have the finished keys. Think of those like a final cryptographic seal on a contract. They're used at the very end to confirm that the handshake completed successfully and that nobody messed with it along the way. So, with the handshake securely completed, we can finally move on to the main event. This is what the entire process has been building towards: creating the powerful keys that will protect your actual data, your passwords, your messages, your credit card numbers, all the important stuff. And the logic here is going to look very familiar.
We take our previous secret, that handshake secret, and we feed it back into the HKDF function. This produces an even more important final secret called the master secret. This is the final ingredient we need. From this master secret, we derive the keys that are going to do all the heavy lifting for the rest of the session.
Okay, back to our diagram for the final move. Follow the chain from the handshake secret, or HS. It's used to derive the master secret, labeled here as MS. This is the ultimate source of security for the whole session. And from MS, the arrows point down to our final products, CATS and SATS. That stands for the client application traffic secret and the server application traffic secret. This is the end of the line. We now have the keys that will protect our data.
And honestly, these are the keys that really matter for your privacy. The application traffic secrets are the workhorses of the entire secure session. And you'll notice there are separate keys for data flowing from you to the server and for data flowing from the server back to you. This ensures that the conversation is completely secure in both directions.
So let's just put these two types of keys side by side to make it crystal clear. Handshake keys have one job: protect the setup conversation. And their lifespan? It's incredibly short, just a few milliseconds. Application keys, on the other hand, have the real job: protecting your data for the entire time you're on the website. The analogy here is perfect. The handshake keys secure the exchange of the recipe, while the application keys secure the final meal you cooked with.
So you might be wondering, why go through all this trouble? Why not just make one key and use it for everything? And that is an excellent question. The answer gets to the very core of what makes this system so incredibly robust. And this is the part you'll really want to focus on for understanding the big picture.
And here is the absolute most crucial point, taken right from the source material. Every single time you connect to a secure website, this entire process happens completely from scratch. A brand new, unique set of keys is created just for that one session, and then they're thrown away when you're done. This is a massive security feature. So if you're studying for an exam, here are the key takeaways you need to nail down. First, the entire process starts from a single initial shared secret. Second, there's a separation of jobs. Different keys are made for different tasks. Third, and this is critical, the keys are temporary. They're created fresh for every single session. And finally, because of how this system is designed, all the keys are cryptographically separate. That means if an attacker somehow managed to steal one key, they couldn't use it to figure out any of the others. And I'll just leave you with this final thought. Now that you know that a completely new, unique set of keys is made from scratch for every single session and then destroyed, what does that mean for someone trying to eavesdrop? Imagine they record all your encrypted traffic. Even if they spend months trying to crack the keys for one of your sessions, all they get is that one session. The next time you connect, there's a whole new set of keys to crack. For an attacker, it's a never-ending battle that they are fundamentally designed to lose.